So, hello everyone. Today we are heading to solve some problem in the chapter 12, which is related to numerical approach for estimating the natural frequencies, including Rayleigh approach, Rayleigh approach, and Holzer method. So firstly, I'm gonna solve question 12.2. It says using Rayleigh method, estimate the fundamental frequency. Fundamental frequency, it means the natural frequency. The fundamental frequency of the lumped mass system. The Rayleigh method is a good approach for determining the fundamental or natural frequency of lumped masses. And basically it estimates and it become close to the natural frequency from upside. For example, if the natural frequency is 50, it approaches from 60, 58, 55, 54, and tends to approach to the natural frequency from upside. So the system shown here is basically, there's a lumped mass system, there's a beam like this, there's two disks, M1, and the second mass is M2. Attached to constraint. So this length is given basically. Hello, Yasin.
Hi, good afternoon.
Good afternoon to you. So in this session, we are going to finish the chapter 12 basically, which is related to obtaining the natural frequency using numerical methods such as Rayleigh for the lumped masses basically, and also Rayleigh and Holzer method. So the first question is 12.2, using Rayleigh method. It says the question, using Rayleigh method, estimate the fundamental frequency of the lumped mass system shown here. The fundamental frequency means the natural frequency of the system. And this length basically is given. This is L over 3 and L over 3 and L over 3. So, and M1 basically is given as 2M2, and EI is constant throughout the whole beam. And for the Rayleigh approach, says that for lumped masses, summation of maximum kinetic energy is going to be equal to maximum potential energy for all masses, according to the equation 12.1.17. The U max is going to be 1/2 G. So we take advantage of principle of superposition. So we consider the effect of each mass on the beam individually. So if you want to consider the effect of M1, you have to remove M2, M3, M3. So we consider the summation of effect of, we consider the contribution of each masses individually and separately and make a summation at the end. For example, the potential energy of the whole system is going to be the first mass, its corresponding deflection Y1 plus M2 Y2 plus M3 Y3 plus, and also equation 12.1.18, it goes to T max is going to be 1/2 omega squared M1 Y squared plus M2 Y2 squared plus M3 Y3 squared. So from the two equations, we could draw a conclusion that first omega 1 squared is going to be U max, T max, the fundamental frequency or natural frequency, is going to be equal to G summation of mi yi from I to n, number of degree of freedom system, and summation of mi yi squared. So this is the formulation, and all you have to do is just calculate the deflection. So if we have basically a system like this being subjected and mount on a two constraint like this, and there is a point load W, suppose there is a point load W, and consider these lengths as, so X, these lengths as basically B, and the whole length of the beam is L. And if you want to calculate the deflection at any point like this, like X, this point, or this point, or this point, the deflection for this configuration, be careful, for this configuration where the point load has a distance B from the other side, while at the other side, in the left side, at any point like this, the deflection is going to be W, the magnitude of the point load, multiplied by B, the distance of point load from the other constraint, X, the distance from the left constraint to a specific point, like I said, I colored by green, divided by 6 LEI L squared minus X squared minus B squared. So you have this equation in the book in the chapter 3 or 2, I don't know, chapter page 46, I think. Page 46, you have this formula, and deflection at any point due to a single load W at a distance B from the right side, right end, at a distance X from the left side. So by using this equation, you could find the natural frequency of the system according to this formulation. All you have to do is just finding basically Y1 and Y2, because you are given M1 and M2, and you have G, and then you could easily find the natural fundamental frequency or natural frequency omega 1. So how can I find Y? Since I have two masses, I'll have Y1 and Y2. Deflection basically at point 1, deflection at point 1, and deflection at point 2. Deflection at point 1 is a function of M1 and M2. It means that not only M1 will contribute to the deflection at deflection at 1, but also the M2 will contribute deflection for the point 1. And also for the point 2, the total deflection is a combination of effect of M1 and also M2. So for each point 1 and 2, we have to consider and calculate the contribution of each masses and then make a summation. So just focus on Y1. Deflection at first mass. So deflection due to for the first point 1, deflection due to firstly deflection due to the main mass m2, which is 2m2. So in this case you have to forget the second mass, and all you have is basically a system like this. The first basically the first mass, effect of first mass on the left point. So here to M2, which is M1, and suppose this is a deflection of due to only these masses, and let's call these lengths y prime 1 and this length y prime 2. So the first mass has can affect the deflection both at point 1 and 2. You have the formula, you could easily obtain the corresponding deflection. So y prime 1 is going to be point W. W is mg. So 2m, 2g is the W. Okay? And basically x is, so we have to take a look at from this side for the equation. So the x is this length. This is x. So 2/3 L is the x, and B is the distance from the load point to the other constraint. This is B for this case, right? So B is L over, oh, sorry, I made a mistake, Bx. So B is, the formula is Bx, okay. B is this is B and this is X. So B is 2/3 L and X is L/3 multiplied by L squared minus X squared minus B squared. B is 2L3. So finally I will reach to this point equal to 16,486 M2G L cube divided by EI. So similarly, by taking advantage of this equation, you could easily find deflection at point 2 due to the first mass. Deflection at point 2 due to the first mass. So mass W is mg, 2m2g is W. And so here, for the second case, it is the x, and the, okay, x is L/3, and B also, B is constant because the point load is constant. B always is L/3. So L/3, distance is L/3. So L squared minus X squared minus B squared. So this is going to be equal 2, 14, 486 M2G L cube EI. So similarly, you have to find the deflection due to the second mass M2. So you have to remove the first mass and just consider the effect of second mass M2. So as soon as you put M2 on the beam, the beam deflect like this. This is Y second 2 deflection at point 2 due to the second mass, and this is deflection at point 1 due to the mass at or point load at second mass. This length would be B, and these are going to be basically X. So Y second 1. So W is mg. X from the left side is this point, L over 3. B is distance from the point load to the right is L over 3 divided by 6L EI L squared minus X squared minus B squared. Totally it equals to 7 over 486 multiplied by M2GL cube over EI. So deflection at point 2, W is M2G, B is this length, and X is here 2 over L. So B is L over 3 is constant for both. 2L over 3 multiplied divided by 6 LEI L cube minus L over 3 squared B squared minus X BX. So X minus B X is 2L minus B squared BX. So it's going to be 8486 multiplied by M2GL cube over EI. So you have to add them up, therefore Y1 is Y1 prime plus Y1 second is going to be 23 over 486 M2GL cube EI, and Y2 deflection at point 2 is Y2 plus Y second 2. It's going to be 22 divided by 486 and 2GL cube over EI. So fundamental frequency would be, according to the equation, omega 1 squared is going to be G summation of mi yi divided by summation of mi yi squared. Therefore, G, the first mass is 2m2, y1 is obtained as 23 multiplied 20 over 486 plus second mass is m2 multiplied by y2, 22 over 486 divided by m1 y1 squared. y1 m2 is m2, the second mass, multiplied by second deflection squared. So there is a factor out here in the denominator. There is a factor out in the denominator, the term m2gl cube over ei. It's going to be 2143 ei m2l cube. Therefore, omega of 1 fundamental frequency would be 4.63 square root of ei over m2l cube radian per second. This is how we obtain the natural frequency. The fundamental frequency is basically lowest omega n. So the lowest omega n fundamental frequency using the Rayleigh meter for lump masses. Question 12.2. Just let me know if you have any question.
I'm okay.
Okay. So the next problem would be 12.23. 12 point. The Holzer method. And one point here for the Rayleigh usually approaches Rayleigh method. Estimate the natural frequency and approached fundamental frequency omega 1 from the high side, It means a little bit overestimate the natural frequency. So there's one point here. So the Holzer 12.23, the Holzer method. Let me just firstly draw the system. There is a 4-disc rotational system, 4-disc. Disc 4, disc 1, GA1, J2, J3, J4, torsional stiffness 1, torsional stiffness 2, torsional stiffness 3. And suppose each of them can have a deflection, rotational angle theta 1, theta 2, theta 3, and theta 4. So the Holzer method, in the first session, I told you that the difference between the force are free natural frequency. Basically, one of the characteristics of the free vibration is that as soon as you apply initial deformation, initial velocity or initial displacement, and then release the system, the mass and the system vibrate, and the frequency that the system vibrate is the natural frequency. And if there is no any external force, it will be vibrate and without any decay, right? So for the free vibration, there is no external force, right? Zero, external force is zero. So I apply an initial displacement and then release the system, it will be vibrate, right? So there is no any external force. And this vibrate only at natural frequency. So Holzer see this phenomenon from the other side. It says at only natural frequency, the system, the focus for the Holzer method is just undamped system. Be careful. So for the undamped system, it says that either linear or rotational, no matter, just undamped. Only it says, Holzer says this phenomenon from the other side. So it says that only natural frequency can satisfy this equation. Only natural frequency causes vibration without any external force. So these two statements are the same. So we have to, using trial and error technique, we have to give some natural frequency randomly, 100, 200, to see if at which given arbitrary omega, the total external torque or the total external force is going to be zero. So the technique here is that suppose we have 4 masses, 1, 2, 3, 4, either linear or rotational. You apply a unit deformation or unit angle or unit displacement at the first mass, and then calculate the displacement or rotation at the second mass, and then the theta 3 or displacement 3 at the third and the fourth, and calculate the force 1, force 2, force 3, and the last force, torque 1, torque 2, torque 3, and the last torque. If the last torque becomes zero, the chosen frequency at the first point would be the natural frequency. So you have to take advantage of trial and error method. So here we want to find the natural frequency for a torsional system containing of 4 disks, taking advantage of Holzer method. In order to apply the method, you have to have the formulation for theta 1, theta 2, theta 3, and theta 4, and relate them to the torque 1, torque 2, torque 3, and torque 4. If you had 4 linear spring mass system, you have to relate x1, x2, x3, x4 to the force 1, force 2, force 3, and force 4. Because you only have to give one random solution to the first mass and then calculate the rest from the first step. So here is the example. In order to have the relation, I will take advantage of the Euler formula for the torsional system. So summation of forces applied to the first disk is I theta double dot 1. So if I rotate the left disk, only K1 will oppose these torsional movements. So it's going to be minus K1 theta 1 minus theta 2. So similarly, you have to apply Euler formula for the second disk, which is equal to J1 to J2 theta double dot 2 is going to be, so as soon as you rotate the second disk, both K1 and K2 will oppose the motion. Note that K1 and K2 both relate to the 2 point, and you have to consider a relative deflection because K1 is connected J1 and J2 and K2 connected J2 and J3. So you have to consider a relative displacement in order to find total deformation applied to the K2 and K1. So minus K1 theta 2 minus theta 1 minus K2 theta 2 minus theta 3. Theta 2 minus theta 2 minus theta 2, theta 1, theta 1. So similarly, you have to write the equation of motion using Euler formula for the third disk. Like this, summation of momentum applied to the third disk is going to be J3 theta double dot 3, which is going to be minus K2 theta 3 minus theta 2 minus K3 theta 3 minus theta 4. So summation of momentum applied to the force mass is going to be J4 theta 4 is going to be minus K3, again theta 4 minus theta 3. So by manipulation these four equations, I could reach to this point. I can reach to this point. Okay, in order to further simplify, take a look at the left-hand side containing acceleration. We could somehow relate acceleration to the displacement by assuming a harmonic motion. Suppose the excitation is harmonic. So therefore, theta double dot would be minus omega squared theta. So their response basically can be written as in a sinusoidal form like this. Therefore, by using this assumption, I can further simplify this equation minus J1 theta 1 omega squared minus K1 minus K2 J2 theta 2 omega squared minus K1 theta 2 minus theta 1 minus K2 theta 2 minus theta 3 minus J3 theta 3 omega squared minus K2 theta 3 minus theta 2 minus K3 theta 3 minus theta 4, and similarly minus J4 theta K3 theta 4 minus theta 3. So if I make a summation, the left hand side and the right hand side, you will see that at the end, so you could multiply the both hand side by -1, and you will have J1 theta 1 omega squared is equal to K1 theta 1 minus theta 2, J2 theta 2 omega squared is going to be K1 theta 2 minus theta 1 plus K2 theta 2 minus theta 3 J3 theta 3 omega squared is going to be K2 theta 3 minus theta 2 plus K3 theta 3 theta 4, and the last one. So if I make a summation here, summation of Ji omega squared theta I is going to be 0, because this will be cancelled out by this, and this will be cancelled out by this, and this term will be cancelled out these two, and only omega n will satisfy this equation, and you have to find that. So the Holzer method basically says that we assume an arbitrary value of omega. So assume first step, assume omega 1, arbitrary, 100, 1, 10. So like for example 10 or 5, for example 5 rating per second, and the second step is consider the first deflection or the first rotation as 1, and then calculate all other deflections. And then calculate and assess, basically assess whether the last force or torque is 0 or non-zero. If it is 0, the omega 1 you chosen is the natural frequency. If it is not, you have to assume another omega 1 and repeat the whole process. Because as I said, when there was a system like this without any excitation, without any external torque or external force, only natural frequency will satisfy this equation, and as soon as you apply any displacement initial condition, the system will vibrate at its own natural frequency. So you need to have relation between theta 1 and T1, theta 2, T2, theta 3, and T4. So just take a look at the first, by by manipulating the first two equations. The first two equations. So here, the equation 1, J1 theta 1 omega 1 is omega squared K1 theta 1 theta 2. So here I can say theta 2 is theta 1 minus J1 theta 1 omega squared K1. So you assume omega. Theta 1 is 1. J1 is given. K1 is given. Theta 1 is 1. Therefore, theta 2 is obtained, right? This is the first equation we need to use. And similarly, if I insert this equation to the second equation, if I plug in, so if you see some theta 2, just insert this in the second equation. So here is equation 1, equation 1, equation 2, equation 3, equation 4. Okay. So put this into equation 2. Therefore, J2 theta 2 omega squared would be K1 theta 2 minus theta 2 minus. So here, remove the theta 1. So theta 1 is this term added to theta 2. So theta 2 here minus K1 theta 1 omega squared K1 plus K2 theta 2 minus theta 3. So this is theta 2 minus theta 1, right? This was theta 2 minus theta 1. Theta 1 is theta 2 plus J1 theta 1 omega squared K1. Just plug in here. Theta 1. Therefore, J2 theta 2 omega squared would be finally minus omega squared J1 theta 1 plus K2 theta 2 minus theta 3. Okay, so therefore we are trying to isolate theta 2, okay, from this equation. So K2 theta 3 K2 theta 2 minus omega squared J1 theta 1 plus J2 theta 2. So at first step, we obtain this relation. We have theta 1. Theta 1 is always 1. We obtain theta 2. Then we need a relation. By having theta 1 and theta 2, you have to obtain theta 3. So here we are trying to isolate theta 3, basically. So therefore, theta 3 is theta 2 minus omega squared over K2 J1 theta 1 plus theta 2. So in summary, I can say like this: theta 1 is 1. Theta 2 is theta 1 minus omega squared J1 theta 1 K1. Theta 3 is theta 2 minus omega squared K2 J1 theta 1 plus J2 theta 2. And similarly, theta 4 would be theta 3 minus omega squared K3 and J1 theta 1 plus J2 theta 2 plus J3 theta 3, right? If we had 5 mass, theta 5 would be theta 4 minus omega squared K4 J1 theta 1 J2 theta 2 J3 theta 3 plus J4 theta 4. So we have only 4 masses. So this is how you have to relate theta 1, theta 2, theta 3, and theta 4, and you need to calculate torque 1, torque 2, torque 3, and torque 4, and you have to only check the last torque T4, whether it's 0 or not. So we call torque 1 J omega squared J1 theta 1. We call torque 2 as T1 plus omega squared J2 theta 2. T3 according to the whole, therefore T2 plus omega squared J3 theta 3, and the last torque would be T3 plus omega squared J4 theta 4. According to the Holzer formula, summation of the left side T1 plus T2 plus T. So T4 is a summation of torque according to this formulation. T4 is a summation of 4 torque. So the T4 should be, by this terminology I wrote here, by this term. So T2 is a summation of the first 2 torque. T3 is a summation of the first 3 torque, and T4 is the summation of all torque. J I omega squared theta I is a summation of the number of degree of freedom system is 4. This should be 0 at the end. If it is 0, therefore omega is natural frequency. So last torque must be 0 when the oscillation is free vibration. And we have to find omega that satisfies this equation. This is how you basically you are able to find omega. So in order to start the trial and error method, you have to construct a table, and which prevents you from making mistakes. So you have to draw a table. So theta 1, you assume 1, and you have to find T1 always omega squared theta 1 J1. In the second case, you have to find theta 2 like theta 1 minus T1 over K1. So let's call this T1. So theta 2, and you have to find, as soon as you obtain theta 2, just go for calculating T2. You have T1 omega squared, you have theta 2, just insert here, and J2. The next column is theta 3, theta 2 minus T2 over K2. And then as soon as you obtain theta 3, you will go for finding T3, torque 2 plus omega squared theta 3J3. The last column, theta 4 is theta 3. T3 plus so this is very important, the last torque. And you can reach to last torque by this step. So at first step, you have to give a omega and calculate omega squared. So suppose we make a random selection. So for example, omega is 5, and then omega squared would be 25, right? So theta 1 always is 1, right? You will go for calculating T1. So J1 1223, J1, J2, J3 is given in the question. J1 is J2, J3 is equal to 1.13 kilogram meter squared. However, J4 is different, which is 2.26 K1 and K2. K1 is going to be equal to K2. Both are 0.169 Newton meter. For each radian, you need to apply this torque, 10 to the power 6. K3, however, is 0. You have K1, K2, K3, J1, J2, J3, and then you need, all you have to have is just calculator. So theta 1 always is 1. Theta 1 always, displacement 1 is always 1, always. So always 1. So I have, you have to find T1. T1 therefore would be 28, 25. As soon as you obtain T1, go for finding theta 2, because you have theta 1, you have T1, you have K1. Then you find theta 2 would be therefore 0.98. Then you will go for T2. T2 therefore is so T2 is here. T1 is obtained, omega 5, omega squared 25, theta 2 is obtained, J2 is given. As soon as you finish second column, you will go for third column. You have to find theta 3 at first step. You have theta 2, you have torque 2, you can find theta 3 as 0.995. Torque 3 therefore is 84. Theta 4 can be obtained as 0.9991, and T4 is unfortunately is not equal to 0 and is 141. So we have to, it's not 0, we have to give another guess. So just draw a line to separate the first guess. So let's go for the second case. Okay, let's say my second guess is $160, therefore omega squared is theta 1 always is 1, T1 therefore would be 2.8928, 10 to the power 4. Therefore, theta 2 can be calculated as 0.8288. T2 would be 1.29. Multiply 10 to the power 4. Theta 3 is 0.1. T3 therefore can be obtained as 6. Then the last theta is 0.3 T4. So T4 is not 0. So we have to continue. Still, we have to continue. And you have to give another guess, another initial natural frequency. So suppose I give omega as 300. Omega squared is theta 1 always 1. T1 therefore is 1.0. Theta 2 is 0.3982. Torque 2 would be 1.42. 10 to the power 5. Theta 3 would be minus 44. Torque 2. Torque 3 is 9. Power 4. And theta 3 would be minus. The last torque in this case is minus 0.433, 10 to the power 4 is negative. So here, by just comparing the two cases, that you will see that if I give omega 160, the last torque is positive. If I consider the natural frequency as 300, the last torque is negative. So you could draw a conclusion that your correct guess should be placed between the two, right? So because 0 is between -8 and +8. So all you have to do is just randomly choose an omega between the two. I assume I take 265 multiplied by 94. So omega 1 squared is 70. Theta 1 is always 1. T1 is 7.918, 10 to the power 4. theta 2 is torque 2, theta 3 is torque 3, 1 minus and theta 3 is minus 6661, and the last torque is minus 8.7979, approximately equal to 0, approximately. So you could say this is the natural frequency. So natural frequency omega n, and you could basically continue your assumption. You could continue giving another assumption to find the second natural frequency also. In the question 12, it's basically you have to take advantage of a numerical, you could write a program, write a MATLAB code for this equation, but in the exam, you are not going to ask such a lengthy, very lengthy equation. Just we are trying to understand how we could write how we could obtain basically a natural frequency. You could also write a MATLAB code. So in the question it says that determine the two first natural frequencies and mochi. So the first one is obtained, and the second one you have to continue the given initial guess, and the second natural frequency would be 547.26. Omega 2 is going to be theta 1 is always 1. Torque 1 therefore is going to be 3.3843 multiply 10 to the power 4. Theta 2 is minus 1.0025. Torque 1 minus 805.6. And theta 3 minus 0.99 minus 3.3843 10 to the power 5. Theta 3, theta 4 would be theta 4 with 0.5. T for last torque is minus 2806, which is approximately 0. Approximately 0. So therefore you could draw a conclusion that your assumed frequency is this natural frequency. So second natural frequency. If you write a MATLAB code and draw torque based on omega 0 to 4 multiply 10 to the power 5 is going to be like this. and 400, 500, 600 hertz or radian per second. And you could also calculate the first mode shape from 1 to -1, and the second mode shape so in the system that as I told you, the both hand side is free to move. The first natural frequency is always 0, right? 0, omega 1, and this is the first two natural frequency, the non-zero natural frequency. So this is how you have to obtain the natural frequency using Holzer approach. And as I promise you, I will solve one question for the Dunkerley approach. Just let me know if you have any question for this method.
No, I'm okay. I'm good.
Okay.
Thanks.
So you asked me to solve you one question for a Dunkerley approach, Dunkerley method. I chose question 12.13, Dunkerley approach, to find the natural frequency. Unlike the Rayleigh method, which approaches the natural frequency from upside, the Dunkerley approach from the lower side. So underestimate, a small underestimate, so lower side. From the lower side tends to approach the natural frequency. A small underestimation we could expect using this approach. How you have to see the proof, which is given in the chapter 12. For example, and by taking advantage of basically the influence coefficient, you can reach to this equation 1 omega squared, the fundamental frequency, basically omega 2 squared. So this approach basically says that if we construct the equation of motion mxl plus kx 0, rather than writing k, if I multiply a inverse. So we had basically k minus m omega squared. There was a determinant in order to find the natural frequency, k minus m squared. If I use a inverse as k and calculating the determinant reached to this point. If you, by doing some, you are not supposed to prove that, but by just know that by manipulating and taking advantage of some algebraic technique, you can simplify the determinant like this, plus determinant of k minus m omega squared. So, and k is a inverse influence coefficient. It reached to this point, a11m1 plus a22, the diagonal array, a22m2 plus a33m3 plus annm. Therefore, by increasing the omega, 1 over omega would be very low. So the first one has lots of contribution. You could neglect the rest, and 1 over first natural frequency squared because omega from the response of this equation, omega would be natural frequency. So we basically transfer multiplication into summation. There is a technique. Multiplication to a summation, and the first natural frequency, omega 1, is the lowest natural frequency. 1 over omega 1 squared is the greatest terms in the left hand side. That's why you could neglect the rest term, and the left side, 1 over omega 1 squared, approximately equal to A11 M1 plus A22 M2 plus. That's why this approach is slightly underestimated and approaches the fundamental frequency from the lower side. So this is the technique basically for the Dunkerley approach. 12.13, using Dunkerley equation, determine the fundamental frequency of the beam shown in the figure. So there is a beam like this, question 12.13, W1, W2, W3. L over 4, L over 4, L over 4, L over 4. So W1 is W. W2 is 4W. W3 is 2W. In order to obtain the influence coefficient or deflection at each point, as I told you in the page 36, there is a table that in your book, y at any distance like x from the left side is point bx over 6ei l squared minus x squared minus b squared. This formulation is correspond this configuration. There is a beam like this, these two constraints. The point is applied at the distance b from the right side, and this is going to be a deflection at any point like located at x from the left side can be calculated as this. Therefore, simply all you have to do is just you need natural frequency. You have to obtain A11, A22, A33, A44. A33, because we have 3 masses, therefore number of degree of freedom system n would be 3, and therefore 1 over omega 1 squared approximately equal to A11 M1 plus A22 M2 plus A33 M3. So how can I find A11, A22, A33? Simply just this equal A11 deflection at point 1 due to the unit force at point 1. So unit force P is 1. Basically X deflection B is okay. Okay, so here, if I want to basically calculate A11, so there is a unit force at 1, and I want to calculate this deflection. Therefore, this is x, L over 4, and this is basically B, right? B is 3L over 4. Simply, therefore, you could say that A11 is P, which is 1, B 3 over 4 L X L over 4 6 EI L squared minus L over 4 S squared minus 3 S squared equal to, therefore, so A11 is going to be 256 L cube EI. Similarly, A22, deflection at point 2 due to unit force at 2. So P is 1, X is L over 2, B is L over 2, 6 EI L squared minus X squared minus B squared. Therefore, A22 is 1 over 48 L cube over EI. So A33 is going to be 1 L over 4, 3 over 4 L, 6 EI L cube minus 3L over 4 squared minus L over 4 squared, which is going to be 3 over 256 L cube over EI. Therefore, the first natural frequency is approximately A11 M1 plus A22 M2 plus A33 M3 is going to be equal. So M is W over G, right? W is given. So 256 L cube EI W over G plus 1 over 48 L cube over EI. 4W over G is M2 plus 3 over 256 L cube over EI, and M3 is given, M is W over G, W is 2W for the last mass. Therefore, 1 over omega 1 squared. If I factor out L cube W EI G, I have 3 plus 4 multiplied by 16 plus 6 over 256. So you could calculate 3 plus 4 multiplied 16 over 3 plus 6 divided by 256 is going to be 91 768 L cube the EIG. This is the first basically natural frequency using Dunkerley approach. So just let me know if you have any question.
No, I'm okay. It's perfect.
You're welcome. So basically we are done with chapter 12 and the last, we don't have any more question. So if you have any question, just let me know, or you could bring your question. Next session would be our last session. Just try to solve equations. Try to solve some problems, and if you have any problem, just bring me and I will solve it for you. So now I'm available if you have any question.
No, I'm okay for now. I think I'll try to find questions for Wednesday.
Okay. So next session would be our last sessions, and hopefully you will pass the exam with the perfect score. And
Hope so. Thank you.
You're welcome.
Well, talk to you next session.
Okay, next session. Have a great day.
Perfect. You too.